Are you ready to go? You can start it. Okay, I don't see us on the screen. Okay, here we go.
There we are.
All right. Welcome to the Computer Security Seminar. Today's speaker is Ronda Henning from Harris Corporation, and she will speak on FuzzyFusion, an application architecture for multi-source information fusion. Ronda.
Thank you. I'd like to point out that this is work that I've done. Dr. Kevin Fox, who's currently working a large proposal back at Harris, and the team that was responsible for a system that we called the Network Vulnerability Visualization Architecture. So let's talk a little bit about what FuzzyFusion means and why we came up with why we developed FuzzyFusion. See, everyone says patch management is a very easy thing for systems. Now, in reality, we shouldn't need patches because the software should be perfect when it's released as a commercial product. Unfortunately, we've been conditioned to accept what we get from our vendors and we'll fix it later. Okay? So part of the problem, especially in a large enterprise, is you may or may not know what you have out there on your network. So you have to discover what you have in systems, and you may find wireless access points you didn't know about. You may find whole server farms you didn't know about in an enterprise. And you're sitting here saying, how could that be? And it's like, oh, it's very easy. You know, some people have extra money in their budget and decide they're going to make their world better for themselves. Right? So you have to know what you have, i.e. inventory your systems. And you'd like to know the secure state of those systems. So you do a vulnerability assessment. You want to find out, are these systems patched at the correct versions? Are there large vulnerabilities that have never been patched? And what do we do about them? So you want to find that out early. Once you know what you have and you know the state of those systems, you want to prioritize, right? Because given an infinite number of resources, you can fix anything or everything. But most people have a problem with managing their time and managing their assets. In some cases, if a machine is very old or if the software load is very old, it may be more cost effective to replace it. You won't know until you prioritize what you have. So once you've prioritized that, you want to move on to look at how you're going to fix the vulnerabilities, how you're going to do the root cause analysis. Did I miss a patch somewhere? Did I not patch because somebody was doing some very intense processing on a weekend and I skipped it and never got around to going back to it? You want to find out. And then once I've got it in a known state, I want to keep it there. So I have to continuously monitor it. I have to maintain that compliance with my standards. Because if you don't, you're setting yourself up to start this cycle all over again. And the more cycles you have to go through, the more painful it becomes. And the more people look at security and say, it's one of those hassles and we'll never get it fixed. So this is how we resolve those issues, because nobody wants to go through this kind of pain on a daily basis. And a lot of IT people do go through this pain on a daily basis, so we like to avoid that. So what's the problem that we're looking at? And why do we have that cycle? Well, a network or a network segment has a lot of pieces to it. And this is a small segment. We have some internal LANs. We have an internal network infrastructure. We have some people who come in from remote sites. We have some internal servers. Well, we don't necessarily know where the biggest holes are. And we want to find the holes. And once we find them, we'd like to make sure they go away. So this is the problem that we're trying to solve. But the problem is we've got different types of devices. They all need to be scanned. They all need to be maintained. That's why you do an asset inventory, so you know what's where and of what type. So you can figure out which vulnerabilities apply to a given system. So in a typical data fusion model, data fusion, the bringing together of information from disparate sources, there typically are 4 levels that we care about. Okay? We care about the object, i.e. a given node in the system, right? And you want a consistent frame of reference. You want to know what is a vulnerability, what is a misconfiguration. You want to be able to estimate, and you want to be able to refine that estimation by knowing what's there. You move from there to situational refinement, where what's the relationship between objects? What's the relationship between, I took a power hit last night and I have 5 dead machines on my network this morning. Well, I have 5 dead machines probably because their power supplies were flaky before the power hit, but I didn't know that. I found out when the power went out. Okay? So you look at objects, you look at the environment, and you start looking at the symbolism. So you can bring things together within the context of the environment or the operational problem, i.e., how are you using the systems? How do you pull that together? From there, we look at threat refinement. We look at how do you take that situation and look at vulnerabilities, threats, and opportunities. A threat is a vulnerability that had the opportunity to be exploited. So we pay attention to that and we refine the threats. And then we look at process refinement. How can we make putting all of this information together more effective, come up with better answers? What additional information do I need, and are there places I can go to get it? You want to find those things out as quickly and as effectively as possible. So you can meet your needs with the model as quickly as possible and as economically as possible. Now, if we look at security sensors, what's a security sensor? Security sensor is anything that helps you figure out what a vulnerability is faster. It's anything you can do that will help you be proactive in your security posture by giving you information. So a network map from a network discovery tool will help you because you'll know what's there. A vulnerability analysis based on that network map will help you because you'll know what vulnerabilities apply to those devices. Okay? The probability of loss will help you. Anything you have relative to a fault tree or an attack tree for a given device or a given system segment or a given physical domain will help you because it's all information that relates to the threat posture of your infrastructure. What FuzzyFusion helps with is making all of that information interpretable so that a user or a system admin person doesn't have to be an expert in fault tree analysis, doesn't have to be an expert in reading the common vulnerability enumeration, or an expert in configuration of every type of device on the infrastructure. You want to be able to have the information available and have it be understandable. And that's the whole purpose of using a fusion model. Because these are some other formats. Some things give you very nice graphical data. Some give you very textual information. Some give you the option to do both. And how much information do you want? How verbose do you want to go? If you look at security information management tools, they'll give you lovely bar and pie charts. They'll also give you the option to look at every single syslog entry. So the question is, what do you want to look at 8 hours a day if you're a network analyst? Most people pick bar charts and pie charts. They don't like to sit there and watch one audit record after another scroll by. It's boring. So you pick the format that makes sense. So if I've got all that disparate data, what can I do to make life better? Well, we started looking because Dr. Fox is an expert on information management and information fusion. And he said, well, what if we took this model of data fusion and tweaked it, made it applicable to the world of cyber? And we said, okay, how could we do that? We decided that a level 1 problem or a level 1 fusion in cyberspace would look at running multiple tools against a single node, meaning a single application, a single device, a single infrastructure element, a router, a printer, whatever. Run one set of, or run the tool set, however many you've got or however few you have, against that one type. And look at how I can refine that data. And the way we define nodes was if it was attached to the network, it was a node. This PC is attached to the network, therefore it is a node. This PC is attached to the network, therefore it is a node. Right? And all of the associated bells and whistles under the desk make things nodes. And that's how we put it together. So from there, we wanted to be able to understand what the object's identity was. Right? Refine the estimation, all right? Do we have it named the right thing? And then, what's that mean? Well, that means I have a data point. Or I may have multiple data points around a node. But that's all I have. I have a bunch of separate data points. It's kind of like Christmas. You have a bunch of different presents. They may all relate to one big present. But until you open the last box, you may not know that. Right? You may get elbow pads, and you may get knee pads, and you may get a helmet. But until you open the box and see the rollerblades or the skateboard, you don't know what you're getting for Christmas. So it's that kind of a problem, or not problem, but it's that kind of a scenario. So if I look at level 2, I look at all those pieces together, right? I figure out I'm getting a skateboard, or I'm getting rollerblades, or whatever, right? And I look at the relationships in that segment and how they come together, right? So how do all the different pieces that I've discovered with my tools relate to each other? And how do I take that information and associate it with my computer security goals? I.e., what am I caring about in security? Am I caring about authentication requirements? Am I caring about access control requirements? Am I caring about the network configuration and the protocols that it supports? Have to figure it out. And I combine those results at the network segment level. So the interest there is, what are the vulnerabilities of a given segment? And then, of course, we go up another level, and we look at what's the impact of that segment's vulnerabilities on the whole system, and what's that situation going to look like. That gives you the ability to do what-if modeling. If I change this vulnerability, what's it do to the posture of my whole segment? If I close this protocol hole in the firewall, does it make my world better everywhere? Or will I get more value out of putting a user ID and password on my print server? It's a question of being able to trade them off. And then finally, we looked at countermeasure refinement. Which countermeasures will buy me the greatest amount of protection? Which will give me the highest value relative to the threats in that world? Because the better you can connect and define those vulnerabilities and determine that value, the better and the more effectively you can expend your resources. Because we can't stay awake 24 hours a day. We can't spend an unlimited budget on security. If I'm spending all of my money patching holes, That's money I'm not spending upgrading my servers. That's money I'm not spending for that neat software application that the simulation and modeling group wants. It's a question of trade-offs. And you want to make sure that you optimize your trades to the extent that you can, so that you can do things that will make the system better in the long term. So we came up with a model for data fusion for security. And then we said, okay, if we accept that as the model, how do we implement it? How do we bring this together in a meaningful and relevant way? And we decided that there were a lot of disparate tools. And we didn't want to reinvent them. We wanted to find a way to combine their outputs, but we didn't want to reinvent all of the pieces. So the answer was, can we write a user interface that will allow people to launch the native applications without having to rewrite those applications? So I just wanted a launch pad for existing tools. And what we used as our launch pad was HP OpenView. And the reason we used that was because we got a nice network map. And we used the network map as a way to select nodes that we wanted to run the environment against. We also used that network map to present information to the user, to allow the user to understand which node would give them the greatest value in repairing problems. So out of that, we built a common system model. In other words, we took the metadata from the expected output formats of all these tools so that we'd have a common place to combine that information. So we could take the information from all of the tools and all of the devices and bring it together in one environment. And to do that, we partitioned the analysis and the refinement tasks so that we were doing a refinement task per level. And then, of course, we decomposed further. But because we had a model and we had a tool suite, we wrote this such that it could be expanded. We could add additional tools, and we would have to make some minor changes to the user interface. We'd have to make some larger changes to the common system model to accommodate the outputs. But it was a straightforward process to integrate more tools into the environment. From there, we started working with and came up with our concept of fuzzy fusion. And if you looked at the tools that if you remember the tools we looked at when we talked about sensor data, we had very different outputs. We had network maps, we had words, we had graphics, right? How do I take all of that information and convert it into something usable? Something normalized in the traditional database sense or data modeling sense? Well, what we did with it was convert it into fuzzy facts. And what we mean by fuzzy facts are facts that have been subjected to fuzzy logic. So we make some fuzzy assessments, if you will, to categorize information. And we take that fuzzy data, the fuzzy facts, and our common system model, and that way we can put the information in a common language. Once we have the information in a common language, we can reason about it, and we can reason about how we change it and how we combine it. So that way we can map things from very specific to a more integrated model as we move up in levels of refinement. So we take the tools, after we've taken those results and converted them into fuzzy facts, and after we've validated the results against the common system model, and we export it to our expert correlation component. Now you're going to sit here and say, what do you need to correlate it for? Well, fuzzy facts are still distinct facts. They don't relate to each other unless you tell the system how they relate. And that's why we have export correlation. But we take requirements in fuzzification, and we implement that abstraction that I just talked about. We take that abstraction and we take it and we compare it to the requirements for the system. And what we did for this particular environment that we were talking about for FuzzyFusion was look at using audit, communications, identification, authentication, and access control. We picked those because those are the common areas where there are technical misconfigurations that could be easily addressed in a network. And that was why we picked those requirement categories. So that was how we fuzzified to come up with the fuzzy facts. Yeah, there were a lot of F's and a lot of Z's, but we had a lot of fun doing it. You know, I mean, we started thinking, okay, what are we going to use as the mascot? Thought, let's get fuzzy bunny slippers. Let's get fuzzy bunny ears. Yeah, it was about that time of year too. So anyway, so what we did was look at the first two levels. We took our metrics, we came up with the goals for evidence, i.e. the requirements, and we defined those. We did the data fuzzification, so we had the fact base. Yes?
So I do say a little fuzzy. Sorry. Can you read the boxes?
Certainly. Across the top we have the common systems model and the tool suite results, i.e. the facts. Okay. The three disk-like devices are the requirements database, the security metrics, and the vulnerability database. In this case, we call that the common vulnerability enumeration database. Those feed into the goals for evidence accumulation. Now, along the bottom, we have a fact base, i.e. the information we've collected. We subject that to expert correlation to connect the facts. We have fuzzy inference network rules, because we implemented the fuzzy reasoning and the fuzzy inference with fuzzy clips. Okay, so that's the pieces. So we work on a up and down level on the right side, and we work across the bottom. Okay, so the research was looking at, okay, can we define a node? Can we define a network segment? We figured if we could define enough network segments, we could work on going up in the model. So we looked at taking vulnerabilities and matching them to categories, i.e. how did you know what bucket to put a given fuzzy fact in? And we looked at the cause, the impact, and what the vulnerability was. So we have a simple example here, okay? The example is I have a NetBIOS share, and there's no access control at all. So you can get to the resource, and if you get to the resource, you can own it. You can take everything off of that resource. You can hit format and just say yes. It's a good thing, right? And all your data goes away, right? So the actual vulnerability is that you can get total access to the resource. And it's an access control problem because nobody set the access to what it should have been. Okay? So it's a mapping of the requirement that says access control should be implemented to the system. Okay? So we categorize that based on the vulnerability. Right? What isn't being correctly implemented? Access control to the NetBIOS. We have another example, a vulnerable component. This is from a vulnerability scanner. Okay? The scanner says, FTP can gain root. So, the intruder can get root privileges. If we're sitting in here and it's a security seminar, by now you should know root is a bad thing. Root unconstrained is a very bad thing. Okay? So, this is a piece of software that can make the world very painful. Okay? The component that is our problem here is our friend the FTP software, which could be an add-on network stack, or it could be integrated, depending on the device that we're looking at. Okay? So it's the problem. Now, it doesn't tell you that the weakness is that you can get access to everything. It assumes that you know what root is, right? Okay. So at that point, we talk about what the potential impact can be, that you will own the system. Okay. So we classify the vulnerabilities. They're requirement mapped or they're component mapped. We don't get into a lot of detail beyond that. We started out going down a lot of different paths to categorize, and we came back up to, it all comes down to one of two things. Either you've missed the requirement or the component isn't correct. And that was how we settled for our first iteration. And then we looked at the correlation box, right? How do we correlate all these fuzzy facts and reconcile them with the requirements, okay? So we created fuzzy expert rules. And in this case, we used fuzzy clips as our implementation engine. And the goal there is to take those results that we've put in our fuzzy facts and merge them together. How could you tell that if I have this rating from a tool that assessed system criticality, and this rating from a network map, and this rating from a vulnerability scanner, that if I put them all together, I have a problem? Right? How did you bring that knowledge into the tool at the user interface level? Okay, so that's what the expert correlation component does. And what we did to collect that knowledge base and build that expert system was talk to the people that built security systems. We talked to the security engineering team. Okay, if I have this, this, and this going on, what's it mean? If I only have two fuzzy facts, what's that mean? And figured out a severity that we could associate with the information. Okay, if I have to audit, but I don't back up that audit, or when the audit's full, I don't do anything like switch to a backup audit file, I can't rely on auditing to meet my accountability requirement. I have to find another way. So that's the kind of thing that the expert correlation component gave us. So if I look at that, our level 1 rules were designed to give me a vulnerability rating for a single node. At level 2, I take all of the nodes on a network segment and integrate those. Okay? And I do those by running correlation rules. And we divided the correlation rules into the categories listed on the slide. We had vulnerability association rules, meaning the vulnerabilities associated with a given node. We had mapping rules. Did we have the requirements in the right bucket? We had refinement rules, how we could better merge things, analysis rules, and rules that were necessary for the maintenance of the inference network. Now, if we look at association rules, we used rules to prune the vulnerability space. We didn't want to look at any more than we had to know that there was a problem. If we had a machine that had never been patched, had never had a configuration applied to it, or anything else, we figured out that that was a problem, okay? And we looked at what was meaningful and what wasn't meaningful, okay? For example, if it's a secured building, okay, meaning you had to have a key or a badge or some user ID and PIN to get into the building, it wasn't necessarily the system's fault if you didn't have a user ID and password. So you could, I don't want to say discredit a requirement, so it wouldn't show up as a vulnerability. Because you have the concept of compensating controls. I have a compensating control that says physical access control is implemented. So I'm willing to accept that I don't have accountability in my infrastructure. Okay? And they exist in the format listed here, right? If it's a vulnerability and it's a requirement, then there's a problem. If it's a vulnerability but it's not a requirement, let the user know, okay? If it's a requirement but it's not a vulnerability, and then the fact that it's supported as a requirement is okay. So we found ways to cut down the search space. And those are the three basic categories that we used. Then we looked at mapping, right? How did we have to map, or what did we need to fill out the logical model, okay? And this is what we did through expert correlation in this point, right? If it's a requirement and it's not in the system specification, then I haven't specified the system correctly. Because in theory, every requirement should be in the system specification. If it's not, I have a bad design. If it's in the system specification and it's not a requirement, I should issue an advisory note to the user to let the user know that we think you might be missing something. We're not sure. Okay? If it's a requirement and it's in the specification, then I have the right alignment to proceed. So I want to give the user feedback on what I find, but I don't want to give him unnecessary feedback. If I look at refinement, right, how do I add human information from subject matter experts so I can consolidate the information and build those high-level conclusions? In other words, make use of my human experts so that not everybody has to be one to understand the results, right? So if I have a lot of findings about something, can I aggregate those findings into a general category? Audit is okay, audit's not okay. Audit of devices is good, audit of users is bad. Those kinds of things, right? So, you know, the rules can compensate if you don't have tools that address an area, okay? So aggregating all the pieces into a system of systems or a network segment. There aren't a lot of tools, or there weren't a lot of tools at that time that did that aggregation upward. So we did a lot of that work with subject matter experts and formalized our results into rules. We looked at the rules to refine the data so that we could get to evidential reasoning. And that meant, you know, there could be some places where you had to do probabilities. What's going to happen, right? How are you going to come up with usable evidence? And our explanation for coming up with usable evidence was to use inference networks. So we could reason with heuristics. And the reason we wanted to reason heuristically about probabilities was we wanted people not to need a priori knowledge of either the system or its application. We wanted people to be able to run the tool without having to know everything about the environment. And that was the whole reason for the inference network. To be able to take the things that a human would know and integrate those as rules so that we could turn a less sophisticated user loose with the tool. So finally, we talked about evidential reasoning. Evidential reasoning takes the fuzzy expert rules and gives you that consolidated result so that you can know from a system level perspective what the security posture of a device is at level 1, of a network segment is at level 2. Okay? Facts can support or refute the hypothesis. Okay? You can reject it or accept it, and you have a degree of confidence in your answer. I'm 99% sure this system is compromisable. Or, I'm 80% sure this system is in reasonably good shape. Reasonably and 80% are about right. Okay? So what we did was take evidence from each of the tools to figure out what the overall probability was. Okay? So the assessment data comes into a point of reference, a yes or no, right? So because we provide the criteria, we further reduce the search space. So essentially we perform goal-based information fusion. Now, the answer here is, what we wanted to do with evidence accumulation, right? Was there a correlation between the goal of the assessment and the data you collected, right? So the more we looked at this problem, the more we figured out that what you were trying to achieve with this assessment colored the results you got. I don't want to say you went on a witch hunt if you were looking for network problems and everything looked like a network problem, but that was pretty much where it went, right? So there are a different set of tools and a different reasoning that you apply if you're looking for network problems than systems problems, right? You run a different set of patches for a PC than you run for a router. So just similarly, you would run a different vulnerability scan. So when you provide the goals, you want to get to the desired security posture of whatever you're running the goals against. And I can get goals from my requirements database. Show me a high robust system requirements profile for a Linux workstation. Okay? I can use a computer security metrics database that says, show me all the nodes that have more than N% vulnerabilities of this class. Or I can use a vulnerability database. CERT messages, common vulnerability enumerations, IAVAs, take your pick. But whichever vulnerability sources you use, you want to know where they're coming from, because they all factor into the analysis that goes into your results. So in conclusion, okay, IA vulnerability information comes from a lot of different places, has a lot of different content, looks an awful lot like multi-source data fusion when you start adding up all the tools. And what we did was look at whether or not we could do that data fusion correlation and apply data fusion type algorithms and reasoning to the vulnerability assessment space so that we could get a higher payoff. And the reason I say a higher payoff is not only can you prioritize vulnerabilities, let's look at another way you can use this tool. What if you created a network map in advance of deploying a system and you wanted to know how to configure it? You could run an environment like FuzzyFusion against that design and learn the optimal configurations for the devices by using the tool as a design tool instead of as a vulnerability assessment tool. So instead of using it on a deployed network, you could use it on a as-designed network, as a design environment, to save you having to run or to validate, if you would, the design element, right? If I have an answer that I got from my design task and I build the network and I get a different answer, what did I miss? What's changed? How can I fix it? And I can learn those activities in the course of running FuzzyFusion. And the other thing is that when we took the vulnerability data and we took it apart and split it into the fusion steps that we have illustrated, there we go, here, where we divided it into fuzzification, correlation, inference rules for the network, and evidential reasoning. When we did that division, that decomposition made the problem a lot simpler. It wasn't a case of I needed a subject matter expert to come in and figure out where the firewall had to go. I could figure it out pretty much from what I got back from FuzzyFusion, as opposed to having to have an analyst sit down and say, okay, where's the network come from? Where's the network go to? And having somebody who had the requirements committed to memory go through the system architecture and put it together. It was a much cleaner approach, and it's also a way to bring up apprentice engineers who don't necessarily know all of the requirements yet, because they haven't done this for a long time. The longer you build systems, the more you learn in advance, and the more your experience comes back to either help you or haunt you, depending on how you look at it. So we found that when we used FuzzyFusion, we decomposed the problem very nicely. Whoops. And that decomposition allowed us to do multi-stage analysis because we knew how each device looked. We knew how each network segment could look. Now, we only did layers 1 and 2 in this study. Question was, okay, you've proven that you can aggregate individual components. The next step would be to take the aggregation of those components from level 2 and build the level 3 model. Unfortunately, we ran out of funding before we got to the level 3 model. In the best of all scientific experiments, you take your experiment as far as you can take it with what you have. We were very successful in getting it this far. And it works out pretty well. So, any questions?
Are there any questions?
Gee, nobody asked what am I supposed to do? Sing and dance for the next 5 minutes? I can do that. I don't know. You may not want to see that. That would scare you into asking questions.
All right. Would you rather ask a question, or would you rather have her sing and dance for 5 minutes? Well,
If you heard me sing, you'd understand why I was a computer security person.
then let us thank our speaker.
Thank you.